back to Maths in an Empty Classroom with me, Mr. Southern. This is part 4 of the lesson on implicit differentiation, and in this video I'm just going to be going through an example of finding turning points on an implicit function. So here we have a curve C has equation x squared plus 5y squared plus 4xy equals 2x plus 4. I'm being asked to find an expression for dy dx, and I'm also being asked in part B to find the coordinates at the points on C where dy dx equals 0. So the value of the gradient is 0, I'm finding the turning points. So the first thing that I need to do in part A is I need to differentiate the function in terms of x. So I have x squared plus 5y squared plus 4xy equals 2x plus 4. Okay, just a quick look at this bit here. I've got another product rule, 4xy. So I'm going to say that u is 4x and that v is y, and that du dx is 4 and dv dx is dy dx. Then using the product rule, v du dx, which would be 4y, plus u dv dx, which would be 4x dy dx. Put that in a bracket because what I've done there is I've differentiated the 4xy. And what you may notice if you've looked at the previous videos where rather than 4 the coefficient was 3, we've got the same form when we've differentiated 4xy, it's just we have the 4 instead of the 3, and that's a general thing that's going to happen with a different value there. So I've differentiated this term, so I'm also going to differentiate the x squared, which is going to give me 2x, and differentiating 5y squared is going to give me 10y dy dx, because that's the y function in terms of x, and then on the right hand side it's just going to equal 2, because 2x differentiates to 2, and 4, the constant, differentiates to 0. So let's evaluate what we've got then. We've got 2x plus 10y dy dx plus 4y plus 4x dy dx equals 2. And I've been asked for an expression for dy dx, so I'm going to leave the dy dx terms on the left hand side, so that's 10y plus 4x dy dx. And then I'm going to move the other terms over to the right hand side, so 2 minus 2x minus 4y. Factorise out the dy dx, so that's going to be 10y plus 4x, and that still equals 2 minus 2x minus 4y on the right hand side, and then I can divide by the bracket and simplify. So dy dx equals 2 minus 2x minus 4y all over 10y plus 4x. And you can probably see that I can simplify that because each part of it has a common factor of 2. So I can write my final simplified dy dx as 1 minus x minus 2y all over 5y plus 2x. And that is my simplified expression for dy dx, and that's part A. Now part B is asking me to find the coordinates of the points on C where dy dx equals 0. So I have an expression for dy dx, so the first thing I'm going to do is I'm going to make that expression equal 0. So 1 minus x minus 2y over 5y plus 2x equals 0. And just having a think about what that must mean, well, if we were to multiply up by the denominator, we would just be left with the numerator equaling 0. So the numerator has to equal 0 to satisfy this equation, so I can write that 1 minus x minus 2y equals 0. And what I'm just going to do is I'm going to rearrange that to be x equals 1 minus 2y. And the reason that I've done that is I've now got an expression for x in terms of y, and if I now substitute that into my original function, x squared plus 5y squared plus 4xy equals 2x plus 4, got there eventually, then I can use that to find the coordinates of the turning points. So x squared plus 5y squared plus 4xy equals, if memory serves, it was 2x plus 4, yep, lovely, equals 2x plus 4. So what I'm now going to do is substitute 1 minus 2y everywhere I see an x term in my original expression. So quite a lot of algebraic work here to do, but here we go. So 1 minus 2y all squared plus 5y squared plus 4y, lots of 1 minus 2y. Now what I've done there is I've just put the 4y at the front and multiplied it by the x because we're more used to seeing brackets like this for expansion. And that equals 2 lots of 1 minus 2y plus 4. So I need to expand out and make sure I get every term. Now remember that this 1 minus 2y is going to be 1 minus 2y multiplied by itself. So make sure that you get every term of that expansion. And you should get 1 minus 4y plus 4y squared plus the 5y squared plus 4y minus 8y squared equals 2 minus 4y plus 4. And what I'm just going to do is tidy up the left-hand side before I start trying to manipulate it all in one go. So looking at the y squared terms, I've got 9y squared minus 8y squared, so I've got y squared. And then looking at the y terms, I've got negative 4y, positive 4y, so they've cancelled out. So I'm just left with plus 1. And on the right-hand side, that's just going to equal 6 minus 4y. So what I now have is a quadratic equation in y. So if I move the 4y over, I've got y squared plus 4y minus 5 equals 0. And I can now factorise and solve. So 2 brackets, y plus 5 and y minus 1 equals 0, which means that my two solutions are y equals negative 5 and y equals 1. Now, I need to substitute back in to find x, and it's important that I put it into this form of the equation here, and there's two reasons for that. The first one is it's more straightforward, so let's just do that to begin with. So for this coordinate here, x is going to be 1 minus 2 lots of negative 5, which is 11, which gives us a coordinate of 11, negative 5. And this one here, x equals 1 minus 2 lots of 1, which is negative 1. And that is going to give us a coordinate of negative 1, 1. So these are then the two coordinates on the curve where dy dx equals 0. 11, negative 5, and negative 1, 1. Just a quick word, when we've got those two y values, what we mustn't do is to substitute it back into this equation here. There's two reasons for doing that. One is it's a lot more work, so just don't do it. But the other one is actually if you substitute those values in, then for each of those two values you get a quadratic with two solutions, and one of those two solutions isn't actually one of the points that you want. So you end up with 4 points when there's only 2. So you must substitute it into the one where x is the subject. So just reviewing the process then, we differentiated to get an expression for dy dx. We made that equal 0, formed an equation which we substituted back into the original, and then this all worked out like so. Now just looking at the original question and thinking about efficiency, We had to find an expression for dy dx here because part A asked us to do that. So it was very important that our solution to part A was an expression that said dy dx equals. If we hadn't been asked to do part A, if we'd been simply asked to find the coordinates of the points on C where dy dx equals 0, then it would be acceptable to get to the stage where you've differentiated everything and just substitute dy dx equals 0 into there. And what you should realise, if you just quickly do this in your heads, you'd end up with 2x plus 4y equals 2, which, rearranging divided by 2, would get you to this. So, a slightly swifter route to the same result, if we weren't specifically asked for an expression for dy dx. Okay, join me in the next video where I'll be looking at one example of an index variable, and then that'll be an implicit differentiation done. I'll see you then.